Okay. So we touched on this briefly at the end of class on Friday because someone had asked the question, how close to the actual sum of the series is the area between the curve and the x-axis? In other words, how accurate is, I guess not how accurate, but how does that area compare to the actual sum? And it's a legitimate question, and it leads us to our first discussion on error and summing a series. So that's where we're going to pick up today. So when using the integral test, we can approximate the error associated with a partial sum. When using the integral test, we can approximate the error associated with a partial sum. If the series converges to S, then the error, and I'm going to put in here, I'm going to put in parentheses, or remainder, because sometimes that's what it's referred to, is the remainder. Okay, so if the series converges to S, then the error or remainder associated with S sub n, where R sub n, associated with S sub n when R sub n equals S minus S sub n. Okay, so let's just be clear on what we're talking about there. The S sub n would be the nth partial sum. Okay, if you want to put that in parentheses there, the nth partial sum. R sub n is the remainder associated with that nth partial sum. S is the actual sum, okay? Not that I can figure out what it is, but I'm going to be able to find out a range. And then S sub n, again, is that nth partial sum. So really what we're saying is this. If you take the actual sum and you subtract your nth partial sum, then whatever's left is your remainder, which we call the error. Does that make sense if you think about it? What? Okay, so let me read the sentence again. If the series converges to S, then the error associated with S sub n is bounded by that remainder, that error, lies between 0 and, you have any thoughts what this is going to be? Infinity? It's going to be between 0 and the integral from n to infinity. What does that n represent there? Where well, yes, it's where I'm starting, but it's where I did what here? Where I stopped, exactly, James. It's where I stopped, right? If I figured out the nth partial sum, okay, so let's say I sum together the first 10 terms of the series. then my integral would start at 10 and go to infinity. Do you get what we're saying there? That leftover area between the curve and the x-axis is going to be the error associated with the sum of the series. Okay, so let's do it, and let's do an example, and maybe some of that will be a little clearer. Yes.
Does that mean if you sum up an entire series, you don't have an error for it?
Well, it means that the error would be 0. You found the exact sum. But remember, we can only find exact sums for geometric. So all of the other series, if we're trying to approximate a sum, we can get a pretty good approximation, but there will be a certain amount of error associated with it. Okay, and for this one, the error is going to be whatever is left underneath that curve, the area. Okay. Approximate the sum of the convergent series. The sum from n equals 1 to infinity of 1 over n to the fourth by using 6 terms. What is the maximum error associated with this approximation? Okay, so approximate the sum of the convergent series 1 over n to the fourth by using 6 terms. What's the maximum error associated with this approximation? Okay, so let's do the first part of the problem first. What am I going to do? Okay, so S sub 6, that's what I'm trying to figure out, right? The sixth partial sum. How do I get the terms that I add together to figure that out? From the term generator. Good, Carson. What do I do to the term generator? And do what with those? And add them together, right? Okay, so when I plug in 1, what do I get? 1. Plus, when I plug in 2, I get?
16.
Yep. Right, 1 over 2 to the 4. I'm going to put that there so if you're looking at your notes later, you'll know where it's coming from. Yes?
Why do you add them? Sorry.
Because I want the sixth partial sum.
Oh.
Remember, in a series, that's what we're doing is adding together, right? So then the next one would be 1 over 3 to the fourth. 1 over 4 to the fourth, 1 over 5 to the fourth, plus 1 over 6 to the fourth. Okay. Actually, you can see. So you guys have out your calculators. Okay, so James says that is 1.081 if you add those terms together. So what does my error have to lie between?
0
0
and 1.
the integral from 6 to infinity. Yeah. Let me change. I'll change it to an x. One over x to the fourth dx.
So why did we do the sum?
I'm sorry?
Why did we do the sum if we're like the 1.081 if we're just going to do the integral from 16?
We have approximated the sum of this series. Okay? Anytime we start actually substituting values in for n and adding them together, we are calculating the sum of the series. Okay, obviously we're not going to keep going and add 1 over 7 to the fourth and 1 over 8 to the fourth and 1 over 9 to the fourth because, I mean, who wants to do that? But that's what we're doing. When we sum together any number of terms, we are approximating the sum of the series. Okay, so the remainder or the error associated with the sum will be between 0 and whatever area is left between that curve and the x-axis from the place where I stopped.
Okay, so our sum is just our estimate.
It is our estimate.
And then
This
our
is an
error is
estimate for the sum of the series right now. We have estimated the sum of the series using 6 terms.
Okay, so are we gonna solve it in a
We are. Yep. So that's what we're going to do next. So we're going to do the limit as b goes to infinity of the integral from 6 to b of 1 over x to the fourth dx. And remember, that's the same as x to the negative 4. So when you integrate x to the negative 4, you get what? X to the negative 3 divided by negative 3, right? Okay, so this becomes negative 1 over 3x to the third from 6 to b. Which is the limit as b goes toward infinity of negative 1 over 3b cubed minus negative 1 over 3 times 6 cubed. So as b goes toward infinity, what's this term go to? 0. And then 6 cubed times 3?
648.
Okay, so and remember the question was, what's the maximum error associated with this approximation? So what is the max error? Make sense?
I mean, do you just have to have the partial sum of 6?
You have to stop somewhere. I mean, if you're going to do a partial sum, the directions in this problem said estimate the partial sum using 6 terms.
So it's like a 2-part problem.
It is a 2-part problem.
So like some of them may just ask for that, and then some may ask for the next.
Yeah, or it might say approximate the sum using the first 3 terms or the first 8 terms. You know what I mean? Like it's going to give you a term number to stop at. Okay? And then
That doesn't necessarily help you get the error.
well, it gives you the starting point, right? I mean, I found the 6th partial sum.
Okay.
So my integral has to start at 6 because I've essentially covered everything up to 6.
But we don't really need the 1.081.
Yeah,
That's
we
not
need to
crucial
do
to
the
find.
part.
You need to do the whole part.
It is.
Because they'll tell you you need to use what.
They're going to tell you how many terms you need in order to approximate it. I have to have a partial sum to approximate my error because it's the error associated with that partial sum.
I think they were saying this, but you don't necessarily need the value of the partial sum in order
Like
to
the
calculate
1.0.
Oh, no.
Yes.
No.
Okay, so we don't have to do that step.
unless they ask you
Like, because it
Well, it's
gets.
because it's only answer.
Because
That's
it's
six, you
giving
can
us
choose
that
6, you
limit
can just
for
solve
our
it.
integration problem. And since we know that that's gonna be the maximum error, if that's what.
Okay, I'm with you now. I did not understand what you guys are asking. You want to skip this step and you just want to go and integrate from 6 to infinity. Well, they ask you to approximate the sum.
But if they didn't, we could just.
Sure, skip it. I doubt they're going to ask you that. Yes.
Whenever you do the sum of that, whenever you add just 6 terms, what do you do about the like the area that you lose whenever you only use like 6 terms for it. Does
Like the error going from one point to another point each time.
Remember, we're not dealing with area here.
Well, no, but like, I don't know, the value.
why do you deal with area for the error but not for the sum?
Well, remember, it's not, it is, the integral test remember that it's not as much to do with the area as it is with the decreasing y values. Okay? Because when we're summing together a series, we're summing together the y values at each point, right? We're summing together the y values associated with the integers, okay? So when your y values they're approaching 0 in this particular, that's a decreasing function, right? 1 over x to the 4th is a decreasing function. So the area, this is calculating the area that's remaining underneath the curve. The y values are approaching 0.
What's the difference between area?
This was the 30-minute discussion that you missed the other day. And we don't have time to have it again. We can't. If you want to have it on an individual basis, you can come in and we can have it.
Real life application.
Because we really did get into it the other day. Not into it in a bad way, just we got into the...
You can't just show him the graph with the area and the curve and the points, finite numbers.
Can I keep going for a minute?
Yeah, sure.
And I might need a little bit of time to process how to say that to you correctly. Yeah?
Okay, so that's the max error. Since when you're doing the integral, you're adding all those little points that the integers want to include. It can't be higher than that, and so that's a max error.
So it's including every possible y value. Small.
You could just show him the graph that the area of the finite numbers.
Yeah, but I don't think that gets us, I don't think that addresses this exactly. It's not the same, it's not the same thing. Let me think on it. Then we'll get there. Okay. Okay, so
You ready?
we're still on 9.3, and that is not the word that I'm trying to write.
my father.
All right, so investigating P-series using the integral test. And that stands for power series. Okay, so at your table, I want you to do these problems. We've done most of them.
Is this gonna make life easier?
Should. I mean, there's a method to the madness here. I mean, we're heading a direction. Okay, so I want you to calculate those. And I'm going to look up something to try to help answer